Yes. Thank you. Is the microphone working? You heard me. Now it's working. Well, it's a great pleasure and honor for me to have this opportunity to talk to the trilateral meeting and in fact an international meeting of professional colleagues and friends in the field of catalysis. I am very pleased to be here for the first time to join these meetings, and I consider those meetings as important as the International Congress on Catalysis or the North American Catalysis meeting. Catalysis is a rapidly developing field, and indeed international groups of scientists are involved in it. In the United States, there's a relatively new driving force for catalysis, and that's environmental legislation. It seems that those things that we will have to do in the future are redirecting somewhat catalysis from the traditional petroleum hydrocarbon catalysis to that which deals with clean fuels, NO abatement, and so forth and so forth. But I'm not here to talk on practical matters because I'm an academic, and I've tried to identify with my students what the key issues in catalysis are. And we need to take this projector down. Can we turn down the catalysis? I've discussed this with my students, and we kind of agreed that in everything that they're doing, the key issue is the nature of active sites, the chemical mechanism, the nature of the transition state, and the dynamics of the reaction. Now, what the students have added to it is that this is, in my opinion, and they reserve the right to disagree with me, but they give me the right to have my own opinion. I was involved with the students in this general scheme, conversion of carbon source to a synthesis gas, then to alcohols, mixed alcohols. In one of these catalytic chemistry, methanol and isobutanol or 2-methyl-1-propanol is a major product, our major product. Now we're involved in coupling of these two alcohols instead of going via the standard technology of isobutene plus methanol, giving the MTBE, methyl tertiary butyl ether. We are coupling these two alcohols with all those fascinating other reactions that occur in this system. And you will see from the last portion of my talk, I need this slide back, please. I need that slide back. That the chemistry of these two alcohols gives rise to, it can be controlled by the catalyst. I'm going to omit the whole field of hierarchical synthesis here, because it's a relatively well-developed area in terms of understanding the catalysts and in terms of understanding the kinetics of those sequential reactions, as well as all the way to having engineering models for those two products. So I'm going to spend some time first on the front end of this chemistry, which has something to do with activation of methane, and then I'm going to switch over to the low end of this chemistry, which takes those two products and will couple them to ethers and hydrocarbons. In the activation of methane, in fact, the single crystal work has been quite useful in our understanding of that reaction. I activation of methane by cracking of the CH bond, then followed by stepwise agglomeration of the carbons, loss of hydrogen, stepwise agglomeration of carbons to oligomeric and polymeric carbons. I'm going to address this part of the process. The curve here is in fact theoretical. It's due to Kurtz and Van Santen. And it tells you that under certain conditions you can pin a monomeric carbon, and then you have to overcome a barrier on metal surfaces. This is here for palladium, for the reason that palladium also has a weak palladium-oxygen bond, so that oxidation reactions can be carried out on palladium. And then in the stable situations, of course, polymeric carbon. Van Santen has shown that you can actually hydrogenate these oligomeric carbons back, and thereby, by temperature swing and pressure swing processes, you can convert methane to high hydrocarbons and hydrogen. But I'm going to deal with a very simple reaction that is cracking of methane and subsequent oxidation to oxides of carbon. If we take a defect palladium surface which has steps on it and kinks, and here I must recognize the pioneering role of the Berkeley School, which really used the single crystal surface science to the catalysis community. One takes the system, and of course there are others who dealt with structure sensitive and structure insensitive reaction. One finds that the activation of methane is a structure-sensitive reaction. And in fact, by cracking of methane, one gets hydrogen at temperatures as low as 100 degrees centigrade over this defect surface of palladium. It's extraordinarily easy with only 10 to 11 kilocalories per mole to activate methane on palladium. This is very unusual, and it is not achieved readily in other chemistries at the rates at which this is occurring on metals. If the cracked methane is subsequently oxidized, the product of that oxidation here in the batch type of experiment, TPD experiment, is not water, but molecular hydrogen with a long tail that indicates that the molecular hydrogen has actually diffused from inside the palladium. So the methane has cracked, hydrogen has gone inside, and then at higher temperatures, even in the presence of oxygen on the surface of the palladium, hydrogen leaves and is trapped as hydrogen, and the carbon is oxidized to oxides of carbon dioxide and carbon monoxide. In summary, what we have here is that the chemistry exists for this low temperature reaction, oxidative reforming of methane, carbon monoxide, carbon dioxide, and hydrogen over these crystals. And in fact, that reaction has been realized also over supported palladium. There is interest in replacing steam reforming reaction by oxidative reforming at low temperatures. And this is kind of a experimental underpinning of that it can be done. Now, how do we want to understand those surface processes in detail? And it is to the merit of surface science and single crystals that it does give us unprecedented detail, sometimes unwanted by the practitioners of industrial catalysis, but nevertheless very valuable from a scientific point of view. And the key role in this is played by spectroscopy. Spectroscopy not only tells us about what the species are, but also what the structure of those species are. If we use valence band electron spectroscopy and have a good theory, we can arrive at conclusions about modes of bonding. We study equilibria both experimentally and by thermodynamics. And the dynamics, of course, or kinetics, the most important aspect of catalysis is not only dealing with rates of absorption and desorption, but also with control of catalytic selectivity through relative rates of different surface reactions. I'm going to give a few examples of how we analyze this palladium system. course, in this limited time, one cannot cover the whole field in generality, but I'm going to try to cover some new aspects of one spectroscopy, electron spectroscopy. It is possible now to do the ESCA on very small spots, including angle resolved both core level spectroscopy and valence band spectroscopy, and by rotating the sample with very high energy resolution, very high for XPS, with about 0.25 electron volts resolution, and with a peak position to hundreds of electron volts. So it is now possible to work really with very, very small single crystals in ESCA and get all the information that is contained here and more. I'm going to concentrate on structural information first. There is a emerging way of doing structures by XPS, and there is a hope that the surface structures, can be determined to within 0.01 angstroms. The structural work is based on forward focus diffraction, here exemplified in a scatterer and an emitter atom. The copper is irrelevant because it can be done with any element. This is the atom that emits a photoelectron. This is one that scatters it. There are two mechanisms. Both of them are, of course, part of the diffraction. One, where the photoelectron that initially propagates as a spherical wave is refocused on the scattered atom. That's called forward focusing. And then there are scattering directions which give rise to the diffraction order. Forward focusing is wavelength independent, the scattering is wavelength dependent, and for high enough energy for photoelectrons, the forward focusing dominates over the diffraction phenomenon for the first and higher order. We have used this first for verifying the structure of palladium surface, and of course you can also determine the relaxations of the various metal planes and so on. Here is a diagram that shows, again, I stress with high energy resolution because this would be important in characterizing chemisorbates. When the emitter is a subsurface atom and the scatterer is a surface atom in the first layer, you can see that there is a distance here for the scattering event that goes back to the second layer. There are in fact some emissions that go back to the third, fourth, fifth layer. Then there are, of course, also scattering phenomena where the second layer atom is scattered off the first layer, but the path lengths are not equal for that, for those events. And here is an experimental curve that shows that these scattering directions have been observed quite accurately to within approximately 1 degree, which translates in this experiment to 0.02 angstroms in unrelaxed palladium 0. This is a palladium 100 phase. These phase center cubic lattices, which is 100 phase, are just about the only ones that do not relax significantly. We have chosen this plane for analyzing oxygen chemisorption in some detail. The oxygen structures have been well characterized, and we've looked at the half monolayer C2x2 structure in core level emission of the 3D 5-half palladium. This is the bulk palladium signal which is there without oxygen. By the time that C2x2 oxygen is added, one gets a new emission here, which shows high intensity at large takeoff angles. That indicates that this emission is a surface state, and we will call this bulk state surface state. It's a normal emission, and this is a large angle emission, showing that despite the fact that subsurface atoms are involved here, there is a distribution of these emissions such that those emissions are closer to the surface than the rest. Next slide shows the angle dependence in detail on these emissions. It looks somewhat like the 5 mountains of China here. The normal emission, bulk and the surface state. The one that has a long path here shows more of the bulk intensity and less of the surface intensity, and so on. And the variation of these intensities is that the diffraction that occurs on the surface atoms by the subsurface atoms emissions, but now there are two kinds of the subsurface emissions. One that has been induced by oxygen, and one that belongs to the bulk palladium. If one takes the ratio of these two for 3 subsurface layers, second, third, and fourth, these are experimental points where the intensity of the surface peak has been measured when these emissions were identified as coming from the second, third, and fourth layer, and measured in relation to the reference, which was the bulk palladium emission. One sees that this core level state extends into the core level measured surface state extends into several layers and exponentially decays in it. There is in fact a theory of surface states that says that this is exactly what ought to happen. I have used a schematic model here by Davison and Brindley that was published in the 1960s, where I have used their theory to determine some of the parameters of this surface state. It's a surface state that decays like here. This is a picture really of the wave function, but it is a single energy. That surface state is a single energy shifted by 0.55 eV with respect to the bulk state. It's like having a hydrogen atom with a positive charge here and wave propagating to far distance, but still that wave has a constant energy. And there is an interaction parameter between nearest neighbors that accounts for this kind of exponential behavior that requires that the decay in the Davison-Brindley theory, into which I will not go into detail, be 0.26 electron volts. You can see what the demands would be on theory here to account for these types of very small interaction parameters. But nevertheless, we have an observation here, and we have a schematic model that says that the surface state extends into the bulk. It's induced by oxygen, and it has a single energy of 0.55 eV. That was the core level angular distribution. We're now going to look at the valence band, in which the interaction between neighboring unit cells gives rise to bonding or anti-bonding or non-bonding situation. And clearly, the energy of the bonded state will be lower. The energy of the anti-bonding relationship in wave functions will correspond to higher energy. And the net result of this is the observation of energy dispersion curve through a wave function that depends on the wave propagation vector. There is an experiment which can help us map that energy dispersion relationship. It's an angle-resolved valence band photoelectron spectroscopy done this time with UV light, UV source, simply by measuring kinetic energy and the angle, the takeoff angle defined here. One finds what the parallel component of the propagation vector is in the crystal, and then one can also determine with a little bit more knowledge the perpendicular component by theoretically knowing the so-called inner potential V0. We've done this for our familiar palladium system again. This is now the dispersion when we change the angle, which is then translated to the K vector, which shows there are bulk states. We can in fact experimentally determine that these are bulk states because they are unaffected by chemisorption in the valence band. But there are also surface states which are affected by chemisorption, in this particular case by oxygen. This is the
portion of the valence band that corresponds to the surface states. And if one has a interpretation of this, theoretical interpretation, which we have done on a rather primitive one-electron model, not ideal for metals, but nevertheless one gets an idea about the orbitals that are involved in this bonding of oxygen to the surface of that palladium plane. We have a fourfold site here. There are all sorts of orbitals sticking out. This is a 4D band of palladium, but the DZ squares have their own symmetry to accommodate the oxygen p orbitals. And the event that I described before is actually corresponding to this kind of pi bonding of oxygen p orbitals parallel to the surface with the DZX and DYZ orbitals for degenerate state here. So what we have a picture of now is that the oxygen bonds bind to the surface specifically with the antisymmetrically positioned at the endpoint DZX and DYZ orbitals, and then deep into the crystal, this kind of interaction propagates 2, 3, 4 layers with decaying intensity by interactions of these orbitals with inside orbitals, further interaction with the core level 3D. Next slide. What I've described just now was the behavior of the C2x2 oxygen, but one can go through this kind of analysis for all the surface phases of oxygen on any crystal that is of interest. In fact, if one looks into how small particles will behave, there will certainly be portions that will look like 1, 0, 0. There will be portions that will look like steps, and others that will be trigonal faces. So I'm just giving an example here of what has been done on this particular phase. An interesting observation was that the 2x2 structure half monolayer, before any desorption occurred, has split into 2 phases. A quarter monolayer phase, which becomes disordered, and half monolayer and 80% monolayer, so-called square by square rotated 37-degree structure. This phase transformation was undetected before because it occurs before any desorption has taken place. Yet this phase transformation seems to be important to some oxidation reactions because we cannot get hydrocarbons into this layer or this layer, or we can get hydrocarbons into these rare phase layers. Then at these temperatures, there are 670 and 700 degrees Kelvin, desorption occurs, which I have depicted on next slide, which is fully counted by statistical mechanical theory, such that the explosive desorption occurs from the dense phase, and the tail here occurs from the rare phase. The rare phase is actually more reactive, but desorbs at higher temperatures because entropy is stabilized by its motion. Look at the 50%, the half monolayer event, where we had a simple C2x2 structure to begin with. The phase transformation occurred at this temperature, and what dissolves from that structure is a dense phase and a rare phase. Non-reactive and reactive oxygen in terms of surface catalytic reactions. Next slide. There's much discussion about the ensemble effect in catalysis. We have used this for a control of supply of oxygen to CH residues of palladium, simply by planting a stationary chlorine on these palladium surfaces. But we have observed that not only there is a restriction of the transport or availability of oxygen. In case that much oxygen is available, we have non-selective oxidations. In case that little oxygen is available, we have selective oxidations, and I included these selective oxidations even to control of CO to CO2 ratio in this oxidative reforming. but also the chlorine is through these lateral interactions, which are similar to the interactions that have propagated the electronic state induced by oxygen into the bulk. There is similar interaction between these, both electronic and blue phase, such that the net result is that the oxygen is much more labile. So this oxygen is more reactive and its supply is limited. Ensemble effect is an ensemble effect, and it is a controlling factor of this CO2 catalysis. We have simulated these things by Monte Carlo and compared these partially ordered structures with streaks and disordered features in lead, and with the net result, next slide please, that we were able to account by this Monte Carlo simulation for the CO2 ratio as a function of chlorine coverage on the surface. Well, I have given examples of the methane activation, of the state of oxygen, of the oxidation of carbon residues, at least to the extent that we could make hydrogen, carbon monoxide, carbon dioxide, and control that reaction. There's more to this chemistry because, as you know, the methane is activated on oxides at very high temperatures, and additions of small amounts of metal are needed for pushing the methane activation temperatures to acceptable range, 350 to 450 degrees centigrade. And I'm now going to switch in a few minutes to the lower end of my chemistry, and that is after we have converted all these oxidized, partially oxidized mixture, hydrogen and carbon monoxide, to higher alcohols. I'm going to show a few diagrams of the reactions that are involved in ether synthesis from the two alcohols. These are the people who did not want to commit themselves to my opinion what's important in catalysis. In the reaction of methanol with isobutanol to the mixed ether, water, and also specific dehydration to olefins, this slide simply says that we need to use an acid catalyst, and since I'm involved in heterogeneous catalysis, I'm using solid acids. Bases are catalysts too, but they're not sufficient for the rates and for the type of reactions that occur at the low temperatures that we need. We have explored a large number of organic acid catalysts and inorganic catalysts for this reaction, and I will show first an example of acid catalyzed over natrium H, which is this fluorocarbon sulfonic acidic resin, the chemistry that occurs in the coupling of the two alcohols. We have methanol and isobutanol. At low pressures, the main product is isobutene. As the pressure increases, the isobutene formation is suppressed. The ethers, the mixed ether, is not the MTBE but an IBE, methyl isobutyl ether, is a dominant product. Dimethyl ether is another product. These kinetics tell us something about the nature of the sites that are involved in this catalysis. Suppression here is actually due to self-poisoning of the acid sites by isobutanol. We studied this mechanism of dehydration by various means, and we found that two sites are actually necessary. One that absorbs the isobutyl alcohol, and the other is a free acid site which catalyzes its decomposition to isobutene. And so kinetically we have to have an optimum here such that many of the acid sites are free, not all of them occupied. At high pressures, slide back. At high pressures, we're occupying both of these sites, and the catalysis will not occur, and so the formation of isobutene will be suppressed. Subsequent reaction, 18 oxygen-labeled methanol with this isobutene gives rise to MTBE, methyl tertiary butyl ether, which is selectively labeled with oxygen 18. That happens at low temperatures. The other product, methyl isobutyl ether, is selectively formed, which is isomer of MTBE, is selectively formed with exclusion of the oxygen 18 that comes from the methanol. And this is an interesting modification of SN2 reaction that occurs on surface sites, both of which are occupied now by the two alcohols, but the reaction occurs such that selectively the oxygen of the methanol is rejected due to steric hindrances that occur on the isobutyl end of the isobutanol on the surface. So we have two isomers. Actually, they're both variable. MTBE, as you know, is an octane enhancer, and MIBE is an octane de-enhancer, but it is a very high cetane number, and MIBE is being considered as a diesel fuel. This is a plot that shows you in the MIBE synthesis that if one adds methanol, then there is an optimal. Too much methanol poisons now the surface sites for the isobutanol. We have a typical competitive kinetics here. Does not look like the SN2 reactions in organic reactions. Those reactions will go like this. So this is a special feature of these surface reactions. The competitive absorption of these two alcohols is added to the SN2 mechanism. The reaction occurs between two sides of the surface. Energy profile has been measured for these reactions. If we start with methanol and isobutanol, we can go to methanol and isobutene. We can also synthesize MIB in water, and either by bypassing to MTBE by the reaction of methanol and isobutene, or by direct isomerization, we can get to either of these two products. These are thermodynamic energies which are very close to each other. These are kinetic activation energies which really control the selectivity of these reactions. Well, I will not tire this audience by showing an awful lot of data, but I can summarize that the acid catalysis is as follows. The organic resins show the selectivity that favors MIBE. Inorganic acids, including this superacid, which works in this case as a Bronsted, not as a Lewis superacid, favors butenes, isobutene. H-mordenite will make selectively in that mixture DME. This is interesting because it indicates that the protons of H-mordenite at these low temperatures, this is a low temperature catalysis, are not accessible to isobutanol, despite the fact that the large channels of H-mordenite are accessible to both alcohol. And in fact, HCSN5 shows poor selectivity with respect to these reactions because it has the acid sites exposed at intersections, whereas in mordenite the acid sites are buried in the side channels at low temperatures. Only at high temperatures will the acid proton travel inside the larger channel and carry out these reactions which are so well known in H-mordenite. I'll have to skip some of these bar graphs which were summarized in the previous slide for shortage of time. This shows the wonderful selectivity to DME. In fact, in some cases, DME is a desired product of this mixture. In some other cases, isobutene or the mixed ethers are desired product. Good selectivity to the hydrocarbon olefins over sulfated zirconia, and a brief summary for the causes of selectivity, which are differences which I already mentioned. H-mordenite displays shaped selectivity such that it picks methanol only at those low temperatures at which the protons are buried in the side channels. Sulfated zirconia is such a strong Bronson acid in this case because the water is a product of the reaction and converts the Lewis acid sites to Bronson acid sites. There is some chemistry over gamma alumina and organic sulfonic resins all behave as lithium H that I described to you. Now where are we in my grand scheme now? I've described to you some front-end chemistry in methane activation. The active site for methane activation was a step on the palladium surface, a defect on palladium surface. The active site for oxygen was a plane surface, but what was formed was a surface state that extended several layers, and this was proved by Esca diffraction into several layers. This indicates to us that the metals, the interactions, both depth-wise and lateral interactions, will extend several interatomic distances, and there's a new method that offers the opportunity to do that. We could control the selectivity somewhat by the ensemble effect, but there is an opportunity for improving the ensemble control by having the ensembles better organized, by pre-absorbing hydrocarbons, fluorohydrocarbons with defined structures and burning of carbon. In the acid catalysis, somewhat surprisingly, and perhaps not so surprisingly to most of you, the active site was invariably a dual site. There were two sites there, even for a reaction that was as simple as a dehydration of isobutanol to isobutene, where you would expect that reaction to be occurring on one side only. So this is a dual site. There's no propagation of waves into the material. It's a well-defined classical organic site. What did we learn about the promised transition state? Not very much. The transition state is measured by measuring effective activation energies, but we have to be sure that the barriers that we measure are in fact barriers for single step. There's a great opportunity for theory, and I think the organic chemists have done a lot in that direction to study the transition states, theoretically optimize the transition state, optimize the saddle point, and I'm trying to develop that area in catalysis. I didn't have time to show you some of these results here, but with the use of supercomputers, there is an opportunity for theoretically characterizing the transition state with some degree of reliability, and then compare the results of these computations with experimentally measured activation energy. Finally, what did we learn about dynamics? The most important to me aspect of catalysis. We learned that, well, we are learning it all the time, of course, in catalysis, that in simple reactions, it might be just the control of the bond strength and this ensemble control of transport of one reactant to another. But in more complex reactions, it's a control of relative rate and the reaction conditions, the relative rates and reaction conditions, such as pressure, that control surface equilibria will give us a very good handle on the outcome of the catalytic reaction in controlling its selectivity. I end on that note. Thank you.
Thank you very much, Professor Klier, for your very interesting lecture. I want to accept a couple of questions about the time. So I want to move to the next. Thank you very much for your nice.
Well, here comes the first oral presentation paper. The presenter will be Professor Masaru Ishikawa. Professor Ishikawa is the professor of Hokkaido University at the Catalysis Research Center. His professional interest is metal cluster derived catalyst, CO hydrogenation of oxygenation, and others. Professor Ishikawa obtained PhD from Tokyo University, and then in 1970